So now that we've talked about what a sequence is in general and some different terminology and how we can find some sums, we're going to look at a more specific types of sequence today, which is called an arithmetic sequence. And I know it looks like arithmetic, like add, subtract, multiply, divide. It's actually said arithmetic. And an arithmetic sequence is a sequence in which consecutive terms have a common difference. So when we go from one term to the next, by a common difference, really that means that we are adding or subtracting the same amount both times. We're going to call this common difference D. So if I go from term one to term two, I've added D. And then from term two to term three, I've added D, et cetera, et cetera. When we write the general form of an arithmetic sequence, again, I'm going to say it's AN. So this is our explicit formula for an arithmetic sequence. There's two ways we can approach it. So I'm going to show you kind of the book way, the first way through. So you'll see that sometimes. But then I kind of have a more favorite way too. So I'm going to show you that also. And that's what I'll generally use. So the formal way of defining an arithmetic sequence is that to take AN equals A1, so the first term in the sequence, plus the quantity of n minus 1 times the difference D. So first term plus n representing, if you're looking for a specific term, n is the number of term. If you just want to come up with a formula or an expression for that sequence, then we'll leave it n. So n minus 1 times that common difference. What I prefer is to do this. We're going to see that if we are adding something, or if we're adding the same amount each time, basically we're looking at like a linear expression where that value that we're adding is our slope. So I treat this more as like the equation of a line, y equals mx plus b. So I'm going to define my arithmetic sequence saying that, well, my slope is the d value, whatever it is that we're adding, times n, which is again either the variable n, or if I know what specific term I want, then that's where I'm putting that value, plus, now in terms of the equation of a line, this is where I would normally put my y-intercept. And my y-intercept is when x equals 0. So I'm going to go back for my arithmetic sequence and write it in as a0. So I'm not actually using the first term in the sequence that I've been given, but I'm going to go backwards a term and use the 0 term because that kind of equates to my y-intercept. Now, how are these equivalent? Because if I go back to the original and I distribute in the D, I have A1 plus, this would be dn minus D, right? So we've already got something in common. We both have the dn. There it is, there it is. Now looking at the book version, if we take A1, which is our first term, and we subtract off D, that's going backwards, and that's giving us the 0 term. So these are equivalent expressions, and I would expect you, if you're going to use this formal definition, to clean it up anyway, and that's going to take you straight to what I like to use as my arithmetic sequence, dn plus a0. Okay, so whichever one you remember, I don't care. They're going to both end up looking as dn plus a0. So when I look at some expressions and I want to write them as arithmetic sequences, or I want to define them using their recursive formula, no, explicit formula, I need to know two things. I need to know what is D, assuming that it's arithmetic, although I shouldn't assume, we are going to check. And I need to know from my sequence, what is A0? So D again represents what it is that is being added each time to get from one term to the next. So from 4 to 11, or 11 to 18, or 18 to 25, I can see that I am adding 7 each time. What that does is it helps me also find my A0, because A1 is 4. That's my first term. So my A0, I'm going to squeeze out here. I'm going to have to go backwards. So if this sequence has been built by adding 7, to go backwards to term 0, I'm going to subtract 7. Looks like that would have been negative 3. So A0 is negative 3. So now I can go ahead and write the explicit formula for my arithmetic sequence. And that would just be AN equals 7n, so that's my DN, minus 3, which is my A0. And then you can check it. If you plug in 1, you should get the first term. If you plug in 2, you should get the second term, and then the third term, and then the fourth term, etc. Okay? So let's go ahead and do one more of these. So for letter B, I can see first term is 6, then it goes -3, -12. So when I look from one term to the next, looks like we're subtracting off a 9. So -9 would be my D. And if I want to find my A0, if we are doing a -9 to get from term 1 to term 2, if I want to work backwards, I'm going to add 9. So my A0 must have been 15. So I can say my explicit formula, AN equals -9N plus 15. Now, just real quick, if you were using the book version of this, you're using that first formula, A1 plus N minus 1D. It would look like this, AN equals A1, which is 6, plus N minus 1 times D, which was -9. But again, I don't want you to keep it like that. I want you to simplify it. So then you've got some work to do. I distribute the -9, so 6 minus 9n plus 9, and then I can rearrange it and get -9n plus 15. And you can see it's exactly what we came up with. So either way you do it is totally fine, whichever way makes sense to you. But if you are using the book version, I want you to make sure that you're simplifying it. You're going to get right back to where I'm going anyway. Okay, so I'm going to skip letter C. Let's jump to a different type of problem. So how about this one? If A4, so our fourth term is 21, and our 13th term is 66, I'd like to find the first three terms, and then we're going to find an expression. We're going to find our AN. So I know my fourth term is 21. So didn't mean to do that. Fourth term is 21. There we go. And then I go fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th term is 66. I want to go backwards and actually say, what are my first three terms? So this is, not what I meant to do. This is the setup for the problem. Okay. So remember, D represents how much we're adding each time. And I mentioned earlier, it's kind of like a slope. I would like to know what it is that I'm adding. So if I'm going from term 4 to term 13, how many times have I added on a D? Well, they're 9 terms away, so that must represent 9 Ds. Okay, well, how far away is term 4 from term 13? If I'm going from 21 to 66, those two terms are 45 away from each other. So a difference of 45 in terms is a difference of 9 Ds. Do you see where I'm going here? So if 9 Ds is 45, that must mean I was adding 5 each time. Okay, so let's uncomplicate this a little bit. Basically, what I'm doing is I'm doing a slope formula. Remember, slope is y2 minus y1 over x2 minus x1. And slope is really our d value here. So your y values are the actual terms, 66 and 21. Your x values are the term numbers, 13 minus 4. And that's the same as what I had before, which was the 45 and the 9. So because this is just like a linear expression, I'm treating it like two ordered pairs, finding the slope, and then I'm going to use that value. Okay, so we found D was 5. That means if term 4 was 21, I can go backwards 5 and get 16, 11, and 6. And then I can write my expression. So AN equals, so D, which is 5, 5N. Now I do need to know what A0 is. So if I'm at 6 and I go back one more term, then I've got a 1. So the expression for this sequence would be 5n plus 1, where D is 5. The first three terms were 6, 11, and 16. Okay, so anyway, that's how we can use that idea of being linear here to solve some arithmetic sequences. For this next example, I'm going to leave it to you. We'll talk about it in class tomorrow, but I want to see if you can think about a nice, easy way where you could add up the numbers from 1 to 100. Because this is a very famous historical problem by a small kid named, I think his actually first name was Carl. Carl Friedrich Gauss which just happily rhymes with Faust, spelled differently. But um, so this again was made famous by this. He was supposedly 8 to 10 year old kid in math class where he quickly added the numbers 1 to 100. So I'm going to leave that for you so we can talk about it tomorrow because it kind of tells us where the formula for adding numbers together come from. Okay, so I'm going to jump ahead to the sum of a finite arithmetic sequence. So again, sum, remember we are adding things together. Finite means our sequence ends. And arithmetic, it's specifically like this linear sequence. So we're going to call it S of sub n. So the sum of n terms, so again, we have to know how many terms, that's what makes it finite, is equal to n divided by 2, so number of terms divided by 2, times the first term, a1, plus the last term, which is an. Okay, so number of terms divided by 2 times first plus last. And that will actually give us the sum of the finite arithmetic sequence. And we'll see why that works when we look to see what Gauss did with it. So I want to go ahead and find the sum of the first 20 terms of this sequence. So I need to know three things. I need to know what is n, what is my first term, and then what is my last term. So n, it says, is 20 because there are 20 terms. A1 would be our first term, which is 2. Problem is, I need to know what that 20th term is. I'm going to erase this. This is actually A20 now that I know n is 20. So I need to know what the last term is. So before we even get to the actual sum, we've got to figure out what that 20th term is. And we could follow the sequence out for 20 terms, right? Or we could use what we know about arithmetic sequences to find it. So I'm going to go ahead and say, okay, A20, and I'm just using dn plus A0. So A20 would be D. So what is it that our difference is? And that's 5. I'm trying to find the 20th term. So n is 20. And then A0 would be, what if I go back a term? So if I go back 5, that would be a minus 3. So it looks like A20 is 100 minus 3, which is 97. Cool. So now I got that. Okay, so these ideas are not standalone ideas. We're going to be using the idea of an arithmetic sequence as we go to find sums, etc. Okay, now we can find our sum. So the sum of the first 20 terms, we now have everything we need. 20 divided by 2. First term was 2. 20th term was 97. So that equals 10 times 99. Looks like the sum of the first 20 terms, without having to find all 20 of them, which is nice, is 990. Okay, so again, that only works if it's finite. This only applies to arithmetic because then as we go to geometric, which will be our next topic, we've got some different formulas we'll use.